Can anybody hear me?
Yeah.
Hello? Sorry about that. I pressed the wrong button and kicked us off. So, hi, this is John Unser. I'm the Technical Impact Manager at IACMI. My responsibilities are working with companies to develop new projects and also helping those projects move to commercialization. And this is kind of a new way we're approaching things, is we'd like to get show some of the highlight some of the projects we've got and the outcomes, and feed that off to a lot of the people that are out there in our community. So I'm not going to go too much further, but I want to kind of highlight some of the projects we've got and do some introductions, and then we'll go ahead and get started in this whole thing. So the first project is looking at what we call a 3.2 project, or Dow Forward project, that's been working on since the beginning of this program. Johnathan Goodsell is going to give us some of the work that they're doing over at Purdue, and Dayakar is going to give us an explanation of some of the work that they're doing at UTK. The next project is our Dow Fibrtec project. Come on in. Okay, Fibrtec is going to be presenting today. Robert Davies, the CEO from there, is presenting on their effort to develop a new flexible tow, and then Michael is going to present from Purdue about the simulation work that they're doing on the project. With that doing, I'm going to pass the ball over to Johnathan, and we'll get started in the presentations. If you appreciate it, if you guys would mute, and if you have questions, we'll wait till the question and answer period at the end of the presentations. Thanks, everyone.
Thank you, John. Are all seeing my screen here? Simulation across the automotive supply chain?
We see it.
Thank you. I'm Johnathan Goodsell, as John just introduced. My role here is the Director of Validation in the Composites Manufacturing and Simulation Center. We're the Design Modeling and Simulation Technology area for the IACMI Institute. I think it's fitting today that you'll hear from us and also from our colleagues in Tennessee, Dayakar Penumadu, who also serves as the other cross-cutting technology area in the materials and processes. And together we support the entire institute, both the vehicles, wind, compressed gas storage technology areas, as well as our 150 plus industry partners in executing these projects. And for us, the charge is design, modeling, simulation, seasoned with a fair bit of validation, with cutting edge manufacturing facilities, all housed here in the Indiana Manufacturing Institute, just north of Purdue University campus in the Purdue Research Park. I show here our team. Those highlighted in yellow are folks that have direct responsibility and influence over this project. You can see that what I'm going to show you consists of a large team of workers, many full-time engineering staff to pull off this project. Shown here then is what we call manufacturing informed performance, where we're going to take manufacturing models and let me ask that if you're not presenting, if you would mute, we're just getting some feedback on the line. We're going to take manufacturing models and feed those into the performance and crash models. And the idea here is if we can capture the physics, then we can predictively design with new material systems. For today, I need to introduce you to three geometries that have been of interest to this project with Ford and Dow. The first is a lift gate. The second, a deck lid. Finally, this double dome shown on the bottom is a training or validation geometry that we will use to prove out the technologies, which we've then applied to the deck lid and the lift gate. Now, in the interest of time, I'm going to focus today on the simulations and models to understand this novel material system and to be able to understand the effects of the manufacturing or molding process. Suffice it to say, the output of the molding simulation becomes the input of the performance simulation to understand both the static and crash performance. of this material system, as well as models to understand the assembly when we do multi-material joining, putting together carbon fiber inners with fiberglass or aluminum outers to predict dimensional warpage, shape change, and so on. I won't cover those today, but we'll be happy to talk about those in further detail with those that are interested. So let's start by talking about this material system, which was developed by Dow as a unique pre-preg platelet molding compound. The idea is you take, in this case, thermoplastic, thermoset pre-preg, slit it, and chop it into platelets of a given aspect ratio, and use that as a molding compound, somewhat like a sheet molding compound. In fact, Dow refers to it as a carbon fiber sheet molding compound that then is used to form structural parts. There are two key descriptors that we need to keep in mind when understanding this system. And the advantage of slitting and chopping this pre-preg is that you get a high degree of collimation, the fibers within a platelet, and you get a high fiber volume fraction. As you can imagine, then fiber volume fraction is key, as is the platelet aspect ratio, to understand the geometry of the platelet as well as the platelet orientation. Those will have critical measures on the performance of the as-manufactured part. And the good news is that we have models to treat all of these, the fiber volume fraction, the aspect ratio, and the platelet orientation. Your first question after you've made the pre-preg tape and you've set your fiber volume fraction is, what kind of a platelet should I make? And you can see three different options shown here. We've developed models to understand the influence of the aspect ratio, which in this case is the length to thickness ratio of a platelet. The influence of the aspect ratio on both the processability and the performance. And you can see that as you increase aspect ratio, you increase performance to a point after which performance asymptotes. However, increasing aspect ratio also decreases processability, as you might intuitively imagine. Now, it turns out that for this material system, Dow designed it such that they have a very good blend between processability and performance. The aspect ratio of these platelets is such that they maximize the performance while maintaining maximum levels of processability. That's step number one. Number two is understanding the orientation. Here on the left is an image of an optical photograph of this initial carbon fiber sheet molding compound. You can see the long, almost stick-like looking platelets. We then have passed those through an orientation measurement algorithm that we've developed at Purdue to understand the initial orientation in one of these charges. The colors correspond to the various orientations, and you can see, while not completely uniformly distributed, there are a couple of peaks. Generally speaking, we've got platelets in every given orientation. The key is that we can now take this platelet charge, this charge consisting of these platelets, take this orientation, and now simulate the manufacture of a real part and understand where those platelets flowed and realigned during that manufacture. And here we're going to look at this double dome part initially, and then I'll bring you back to a lift gate at the end. But we're going to do a lot of training on this double dome to understand the effects of flow. So we start with that mat of the pre-preg platelet molding compound. We drape it over a mold, and then bring two-sided tooling together and flow the mat to form a part. I'll note that in our simulations, we account for the effects of reorientation that occur as you take that charge and drape it onto the mold. Shown here then is an initial charge, which is informed from the orientation state that we measured, and then the draping effects. And now I'm going to show you an animation of a simulation of the forming process. You see the two molds coming together and the flow from that initial alignment all the way to a full part. You'd say that this is a successful molding trial in the sense the part completely filled, but then also you'll note that there's formation of what looks like a knit line there at those lateral extremities, longitudinal extremities of the part. Let's take a look at that time-lapse shots, so to speak, of the simulation on the top, and then short shots on the bottom where we've stopped, the folks at Ford and Dow have stopped the press using different thickness spacers to give us short shots as an experimental confirmation of the predicted flow pattern. And I'll note these, the simulation was performed long before the short shots were executed. When we saw the short shots, we were jumping up and down how well those flow patterns agreed with each other. And you'll note that there's a knit line prediction that is confirmed in the experiment in the way that those flow fronts come together. This lends confidence to the simulation, but this isn't enough. Now we can start using the simulation to explore processing options. For example, we can engineer the engineer the final orientation in the part by engineering the charge placement. Let me show you an example where we've initialized a transverse charge on the left and an axial charge on the right. We're going to look at how those two charges flow to fill an entire part, and we're going to compare these two to gain some physical insight. Okay, so now we're running the simulation. We observe again complete fill, but because of the different flow paths or patterns that are taken from the two different charges, we actually result in different flow alignment or realignment of these platelets at the end of the process. To highlight that, I'm going to change the color scheme on you here and show you the final orientation of these platelets as predicted by the simulation. On the left from the transverse charge, on the right from the axial charge, and I've changed the colors such that the red indicates aligned platelets, the blue transverse platelets, and the green is something where platelets in a given region are not aligned either axially or transversely. And I'm showing you particularly the longitudinal alignment of those platelets. You can see that in the case of the transverse charge, you've got significant axial alignment of those platelets, meaning as the charge flowed to fill the mold cavity, that flow pattern caused a realignment of the platelets in the longitudinal direction. However, in the case of the axial charge, we saw no such realignment. You actually see a preservation of the initially random state of the charge. Now, that simple example illustrates the possibility of being able to engineer the final orientations in your part based on what you do with the charge, both the initial orientations within the charge, and then the shapes and the placement of those charges. Of course, to carry out such a study experimentally would be a daunting task, but we can use these modeling and simulation tools to be able to perform such virtual studies and optimize the final properties of the part based on this orientation. Let me show you now the molding simulation of a lift gate. You're seeing from the initial charge state all the way through the filling of a lift gate. And I'll note this is an exercise of the model against a full-scale geometry, proving that the models can work for such large-scale parts. And now we're collaborating with Dow and Ford to exercise these models against the real parts that they have fabricated, doing comparisons and so on. With that, I'm going to bring you back to the beginning and point out that from here we could take the orientations coming out of the molding simulation, feed those into the performance simulation where we capture the interactions between platelets and predict the strength and the stiffness of these parts, and have actually carried out studies where we look at designing virtual materials and predicting the performance variability among the materials with good agreement with experiment, and are extending this into crash applications together with the Ford team. In the interest of time, I'll leave you with the message here, though. that simulation really is language of innovation across the automotive supply chain, where we've been able to connect up all the way from impregnation through the assembly and have the various project partners across the industry and across the universities talking to each other by connecting into these simulations. With that, I'm going to turn the time to my partner, Dayakar Penumadu, who will talk about experimental observations and measurements of understanding this all-critical property of the platelet orientations. And then I believe we will take questions at the end of his presentation. Thank you for your attention.
Thank you, Johnathan.
So just a little bit, Dayakar is going to take over the presentation and should be ready to roll.
Thanks, John. Can you see my screen?
Yes, we can.
Okay. Yeah, as Johnathan just concluded that tremendous progress has been made by Purdue Modeling and Simulation Group to address this complex topic of modeling the flow and subsequent orientation related mechanical properties to molded components. So this part of the work, as a part of the Task 3.2 for Dow project, is addressing validation part of that, where we are looking at the fiber orientation and mechanical properties. My research team includes Dr. Matthew Kant, who is a research assistant professor here at the University of Tennessee, Knoxville, and Hannah Meiser, who is a PhD student. And our group is a part of the modeling and, our group is part of the materials and processing group, and the program director for that has been Cliff Eberly till recently, and now it is taken over by Merlin Theodore. So as briefly introduced to the topic earlier by Johnathan, essentially, if you could think of SMC without fillers, that's pretty much what we're talking about here. We start with a unidirectional tape, which has B-stage cured thermoset here that Dow has generated over a number of years of R&D, and that tape is chopped and made into this intermediate format here on the right, and then that's put in a compression mold and molded to complex component shapes. Here we're going to be focusing on the double dome that Johnathan had shown in extensive detail. So obviously the same problems that we have been having over the decades with SMC still continue. That is, what is the optimum charge? What should be the initial charge? Orientation, and where do you place it? How do you place it? How does it translate to part geometry, and what are the distortions after molding? All of those obviously have to be accommodated, and thus simulations become the critical part of addressing those early on. This slide shows you an example of a molded flat plaque on the left side and complex component, in this case the double dome on the right-hand side. And fundamentally our challenge compared to metals is the following. Much of the material specifications from metals is based on coupon tests from flat specimens that then extend to modeling and simulation. Because of the grain size and typically the processing of the plates, very rarely you want to have highly textured surfaces, so more or less you're starting with a random orientation of the grains, and then subsequently anisotropy is not often considered in metals. Whereas the challenge with composites, as we know, whether it's continuous or discontinuous, is the orientation of the fiber at a given point controls everything, and it becomes even more critical for discontinuous systems. So the properties you generate on simplistic flat plaques will not translate to the real components that most of you are interested in. Here is an example of an optical microscopy of a series of sections that we are identifying here in red location along a cut section, which obviously shows you the complexity of the platelets. The brighter and the darker regions on the right show you the fairly drastically different orientation of the fibers as these platelets are molded into the final component. So the key is whatever database you generate for material cards need to account for this transformation in microstructure. I'm going to show you essentially three location region of interest based computed microtomography data. These are three-dimensional visualization of the platelet orientations. So if I go back to this double dome for a minute, we're going to see samples extracted from the top region, wall region, and the flange region to kind of give you a sense of how the wall and flange vary as compared to a flat plaque. So I'm going to run this video to show you that you see these platelets, they all start off rectangular, as Johnathan mentioned in his simulations, but after molding, there's a lot of three-dimensional curvature, both in plane and out of plane through the thickness. So one has to realistically capture this for predictive properties. But if I play that again, and you have to take my word for it because you're seeing this for a very short time, but the orientations in this flat plaque are more or less random. It's hard to believe when you look at it, but that's how it turns out to be. But if I play, on the other hand, a same microstructure for the wall right now, and you can kind of see fundamentally that there is certain zones of preferential orientation of these platelets depending on the flow of the charge pattern. And similarly, if I were to quickly show you the fiber orientation in 3 dimensions for the flange part, you could see that more or less there is a preferred orientation in the 45 degree. So
yeah, I'm going to be, I'll just be listening to this.
So clearly we can see that there's fundamental differences in microstructure of these materials depending on where you extract them from a molded component versus flat plaque.
The domes.
And just to give you a sense of the size here, this is a coupon samples tested in tensile testing. So you're looking at a width of roughly 1 inch and a gauge section here of about 4 inches. It's a lot of work to generate this data on X-ray computed tomography, but what we get out of it is a very detailed view of fiber orientation. So we take that data and then we use a technique called intensity gradient analysis, and fundamentally what that means is, as I'm showing you with my arrow, this is a bundle of carbon fiber or a platelet portion of the fiber in one of the planes. So if I look at the intensity of pixels that are represented in the fiber versus in the matrix, they have a large contrast. So if I differentiate the intensity contrast, so I will have a large contrast in this direction as opposed to along the fiber. So this is utilized now spatially in 3 dimensions. In this case, we are showing results for 0.7 by 0.7 by 0.1 millimeter voxel size. The reason we chose 0.1 millimeters is roughly the platelet thickness is usually between 50 microns to 200 microns, so this kind of falls in the middle. And these, essentially the color pixels represent the orientation at a given plane, but now integrating the 3-dimensional effect through the thickness, which you cannot see just from the surface. If I were to play a real quick video, just to show you that now I can track the 3-dimensional orientation of these platelets through the thickness with this technique. So that's a kind of a grounding verification for platelet orientation using X-ray computed tomography. And this is an example that Matthew Kant is showing from his work, where if we take the samples from a flange region versus the wall region, the orientation of these platelets is very different, and this essentially controls the mechanical properties. So if you look at the orientations on the flat plaque, you see that probability of a given orientation is very similar across all the angles. So this is the reason why if I take samples in X or Y or a certain angle, the properties will be very similar for flat plaques. But now once you molded the components, you got this preferential orientation depending on where you are, and that would control your mechanical properties. The other challenge with this discontinuous fiber systems is none of the continuous composite mechanics really applies even for testing. Here is an example that shows that if I take a coupon sample out of this region near the flange and the wall, and I do the tensile test, and this is the stress versus strain in tensile testing, and I pick a point here shown in red dots, so roughly it's about 35 MPa. This sample failed about 80 MPa here, so half of the tensile strength. What you see is there's a tremendous localization of strains, and these are measured with three-dimensional surface digital image correlation-based techniques. So if I use this as a strain gauge, that gives you the stress strain curve there, showing a modulus of 51 gigapascal. If I use an entire gauge length, which is typically what you would use, for example, a large extensometer, then you would get a stress strain curve showing a modulus of 28 GPa. So hence, a lot of the traditional mechanical testing techniques are no longer valid. To interpret them correctly, one has to account for these local variations, largely resulting from fiber orientation and matrix-rich regions. Similarly, the same thing is happening at the different location. So if I were to kind of summarize in a high level, how does the mechanical properties vary? You can see here that in tension, if my green curve is for the material samples in essentially flange region versus this blue curve represents from the flak, so the strains to failure are large and the strength was highest for flange, and then were lowest for wall region where there is a lot of misorientation in the loading direction. You can also see that the fracture patterns also show you that. So for example, the wall stress strain curve shows that the localization of the failure is very sharp through the thickness and in plane versus in a flat plaque, you have a lot of mobilization of failure planes that eventually coalesce to a failure surface. So this is an extremely important point. I think we, both Purdue group and Tennessee group is trying to convey to you that these types of systems, you really need to understand spatially the orientation of the platelets, fibers, and matrix-rich regions. We have done similar properties in compression and shear seems to be least affected by the orientation, but compression and tension have large effects. So in the last part, what I would like to quickly conclude is we have developed a new technique called thermal digital image correlation at the University of Tennessee. This IP is being protected by our University of Tennessee Research Foundation, but I want to quickly introduce that to you. So here I'm showing you two plots that came out of the work of Isaac Daniel over the years, whom many of us know from Northwestern University. He's actually about to retire in the next month, but I've derived some of his work in here that shows that this is a fabric that is a 5-harness weave. So if you look at a continuous composite and do mechanical property testing, the strength is extremely dependent on the fiber orientation. And same thing, obviously, we have seen for the platelets and discontinuous SMC-based systems. But one very important attribute we can gain from carbon fiber composites is that the thermal expansion coefficient of carbon fiber along the fiber direction is negative. So when you heat it, they actually contract, and along the matrix direction is fairly large. So we utilize this information in our thermal DIC system we have developed here to derive spatially what the fiber orientation is. It is a cartoon that we are showing that if you do computed microtomography, it takes a lot of time for small volumes to get precise measurements. Optical imaging is even worse. So we had to develop another technique that's meaningful to complement these two, and that's our thermal DIC. So our technique essentially has the components. We have two optical cameras and one thermal camera, and from this information and the anisotropy of the carbon fiber thermal expansions, we derive the orientation. This is a high-level comparison to show that our TDIC works quite well compared to tomography. And this is an example of a molded component that shows you how temperatures are varying as the part is cooling. So we take this into account and then couple that with the measurement of spatially resolved strain. So here is an example of what we could do now for a full-scale part level. So this work was done with collaborators at a scale-up facility in Detroit, Michigan, where we mobilized our TDIC equipment and technology and looked at a chopped carbon fiber material system being demolded, and as that is being demolded, we now obtain the fiber orientations and also the surface of the component, so we can also get geometric distortions. So essentially, in a high-level summary, what I'd like to conclude is, we have a fairly important insight on how platelet and chopped fiber-based systems will work in compression molding and other manufacturing techniques. TDIC shows promise for extending our understanding of fiber orientation assessments, building on optical and X-ray microcomputer tomography systems. And I think the most important lesson I want all of us to take away is that what Purdue Group showed about the integration of manufacturing optimization work coupled with validation on a part scale shows a lot of promise for this type of ultra fast molding applications for automotives and other application space. Thank you.
Thank you, Dayakar. Appreciate that. I think it's a great project, and we're very excited about supporting this project. And I think we're going to have to do maybe one question. And if not, we're going to go ahead and move to, and again, I reiterate that there's no reason can't get a hold of anybody. You can get a hold of me or even any one of these people that are presenting, and we can get questions after the time frame too. So Bob, you want to go ahead and take the presentation?
There's a lot of background noise. There's music, there's been a train, there's all sorts of stuff going on in the background.
We're going to try to mute those as we go. I think the train was actually behind Dayakar, so it was, but not that it was a train wreck at Dayakar. So, Bob, you want to go ahead and take the presentation over?
Yeah, I'm trying. It's not cooperating right now. Just a second. Here, now it's working. All right, let's go to. There we go. Okay, well, thank you, John. Thank everybody for joining us today. I'm Bob Davies, the CEO of Fibrtec. Mike Bogdanor will be presenting in the latter half of this presentation. I'm going to be talking about the who, the what's, and the hows primarily, and Mike will be talking about the modeling and simulation that was done at Purdue. Partners in this project, the who's, DuPont is project leader. They supplied experimental polyamide resin systems that we use to make the prepregs. The prepreg is our trade product called Fibrflex. They also had a rapid fabric formation, a weaveless weave, if you will, weaveless fabric technology that we applied, and that's really the principal investigation of this project. I do need to point out that the polyamide resins in this RFF project may not be a commercial product from DuPont. It was strictly used in this project. Again, Fibrtec produced the pre-impregnated toes using the DuPont resin and a 12K carbon fiber we provided. We also made some 2x212 fabrics using our Fiberflex to compare to the RFF preforms. Purdue University characterized those preforms, the design and development, as well as analyzed the results. Okay, what is a flexible toe preg? And this slide sort of maps out the way we develop the product. We start with structural fibers such as carbon fiber. It can be glass or aramids or anything to survive the melt process.
Don't make me do it. You'll be sorry.
Yeah, and we do have someone talking in the background. And we can use virtually any thermoplastic resin and this process is more or less a extrusion coating process. We developed some proprietary coating technology. The fiber is pulled through this device. It's coated with the resin, and we take it back up on spools to be used in further processes. The toe, if you look at here, pointer here, getting highlighter. If you look on the outside of the toe, we have the resin is impregnating basically just the outer portions of the toe, the outer 1/3, if you will. The inner 1/3 is unimpregnated. This, for example, a typical carbon fiber polyamide toe would be approximately 0.2 inches wide, about 8 thousandths thick. The inner 2 to 3 thousandths is substantially unimpregnated. And what that allows is the toe to be extremely flexible. It is that way, basically, the two surfaces can slide against each other with the unimpregnated toes in the center. Oh, I want to go back one other thing. One thing, comparing this to say a thermoplastic prepreg tape, and people may say that because the core is not wet out, it's an inferior product. Well, that's really not the case. With the resin being substantially where it needs to be in its final resting place, if you will, when you apply heat, pressure, and a little bit of time, the resin quickly migrates and wets out the toe. We've done substantial studies in that area to prove that. We get virtually void-free or very, very low void parts. Now, again, this slide sort of depicts the differences between a flexible toe and a rigid tape, if you will. The toe can be tied in a knot and doesn't break, which has been someone who's in the textile processes recognizes that as a way of testing yarns for weaving or braiding technologies. Tapes, obviously, if you try to do that, they snap and break. The toes are put up on spools, similar to what the tapes are. But the downstream processes, our toes can be put into preforms that are very flexible. You can see in the lower left corner a fabric which is a 1100 Tex fiberglass with a nylon 6 resin. Is very conformable. Compare that to organo sheets or other rigid structures. So the bottom line is the Fiberflex enables solutions that work. You can make complex and imaginative parts with this, and the designers do not have to force their design to fit the material. Okay, now freeforming, and this is really where the rubber meets the road. How can you use these materials to solve real world problems? Well, with this material, it can go from inventory, not knowing what its final resting place is going to be. It can become a fabric. It can become a braid. It can be used in toe placement. In fact, in the center, you see some preforms developed with tailor fiber placement. The lower photograph shows a piece of Fibrflex fabric where we've tailor fiber placed toes directly on the fabric. This could be used for developing ribs or other reinforcement structures in the tool. The material can also be used in pultrusion. It could be used in filament winding, virtually any process that's available in the composites industry can be applied to this material. This material can be applied to it. Well, that was the end of my horn tooting. A friend of mine, Paul Pendorf, many of you know, says if you don't toot your own horn, no one's going to know you. Now we're going to talk about the project here. This is a slide that shows how we develop the rapid fabric formation. This is RFF for simpler terms. But if you look at the upper left-hand corner, there's a slide that shows toes running into, we'll call it the zero direction. Each one of those colored strands represents a toe, and they're laid down at a specific spacing. And in this case, that's 1/4 of what we call the unit cell. And then the opposite direction fiber, the 90s in this case, are placed on top of that with a similar spacing. And then you come back with an offset and place the toes in the opposite direction, and so on and so forth, till you get a completed cell structure, as you can see on the right-hand side, which is what we call a 4x4 toe cell. You can also see little black dots. Those are where the toes are thermally bonded, if you will, point bonded, to maintain the integrity of the preform. Now you can see on the lower left-hand corner, that's a fabric, an RFF fabric made with our Fibrflex toe. And then also point out what one of the beauties of this technology is that you can make near-net shaped products rather than having fabrics, which would conserve material considerably. And that's what we're showing in this slide here. Now, what are we going to do with these things? This next slide points out a couple of parts we made. I had a tool that we developed a number of years ago to demonstrate a composite, a carbon fiber enclosure, electronic or computer enclosure for the military. It was being built in production using machined aluminum, and they wanted to compare the weight and the strength of carbon fiber to the machined aluminum part. This is an IRD program. What was beautiful about this part is you can see that there are very steep walls in this tool, and that was because we were competing against a machined aluminum, which was virtually 90 degrees. We did make these roughly, I think, around 2 degrees draft. But it also has many other very interesting contours. At the top, you can see on the left side is a 2x2 12 fabric preform. There's 3 plies there. That 3 plies makes a 45 thousandths wall. On the right, we have the RFF preform. So they're both placed on the male portion of the tool. The female portion was laid on top of that, manually pre-compressed. We placed that in an oven, brought the tool to the melting point of the resin, transferred it to a compression press, and applied pressure to close the tool, cooled it apart, and at the bottom you can see the results. The fiber completely wet out. These things rang like a bell, so they're very well consolidated. We were quite pleased with it. Both parts formed well. There were some significant difference, and that's what Mike will be talking about next. Okay, Mike, it's yours.
Great. Let me take over here.
Okay.
Hopefully do this somewhat seamlessly. So while this is loading up, let me just say that, it's been really great working on this project with Fibrtec and with DuPont. Bob, he's able to toot his own horn, but just to do that as well, he's been a really great project partner on this, bringing a lot of experience from, how does the coated toe itself work, but then also the molding processes that we're looking at, some of the comparisons between the new products that we're developing within this project and how they kind of fit within the realm of things that are already in existence. And then DuPont as well, bringing the RFF technology, the experience with the polyamide resins, and being able to say, okay, here's what we can produce. But one of the questions we have on this project is, as we get new material forms, as we get new ways to make a composite material, how do we design a part for that? How do we make sure that we start off on the right foot with that design so that we're confident in a part that we can make with that technology that'll actually meet the needs of the project that we have? So can you all see the presentation? Is that loaded up now?
We do not see your presentation yet.
You cannot see my presentation yet.
Now we see it.
Now you see it? Okay, great, perfect. So one of the questions, we have, how do we design a part using a material system that we don't have a lot of experience with yet? So that's where, as Johnathan introduced this concept of manufacturing informed performance, that's where we can use that to our advantage with a new material system. So if we start with something like the MNT enclosure that Bob was just showing, we have a design for that we start off with the CAD model, and we want to know, how do we go through our manufacturing process and how do we get to performance on that? So one thing we want to do is we want to model the forming process. So orientation state, as we've talked about before, is really critical in these parts, but also the shearing behavior, how it introduces wrinkling, how it shows those different effects, and how that's going to be different between the RFF fabric, since we don't have the interweaving of the toes as you would have in like a twill fabric. It's going to have a different shearing behavior that we want to understand. And one thing that we can do with that is develop a computational model that gives us an understanding, if we go from the coated toes to a fabric, what are the draping properties of that system going to be? So we have a model that we can use to predict that behavior, and then we want to bring this to performance. If we have some type of loading cases, if we have a maximum strength that we need to hit on this, how can we be confident that our first goes at a prototype are going to be as close to getting our results as possible? So that's where being able to come in with a mechanical model that shows, okay, as we get the interaction between adjacent toes, as we get all that information coming in, what is our homogenized behavior coming from this composite that has the resin, that has the fibers, that has the complex mesostructure of the RFF? How do we use all that information to give us a better design? So, going from the design to the performance using the manufacturing process, we're able to get a better understanding of how the process is going to affect our final parts, and then also be able to explore that design space more rapidly. So what do we do if we change our fiber volume fraction? How can we change the bond locations in our RFF so that we get different draping properties that give us better performance at the end of the day? How can we bring all those things into a computational study to give us a leg up in that prototyping process? So here I'm going to show kind of how we tie those experiments that we're doing in with the simulation. So we've been responsible for doing characterization of the material, both in the unconsolidated state before we go through draping, but then also in the consolidated state. Bob talked about how the coated toes are going to have a resin-rich area on the outside and then kind of a dry area in the middle. So how is that going to be affecting our draping behavior? How does that affect the flexibility? We can go down to that level of a model to show how does an individual toe bend, but we can also tie that in with characterization to say, okay, here's our kind of standard fabric measurement techniques that look at bending, to look at the flexural behavior, and go through characterizing that so we can build up our model of the flexible fabric and use that to compare with some picture frame tests of a limited number of cases to compare with and validate our simulation to say, okay, if we have an understanding of the way that this physical system behaves, and our simulation matches that for a couple cases, we have confidence that it's going to match kind of our, our interpolated cases as well. Then we build that flexibility behavior, that draping behavior into a forming simulation, and we can compare those forming simulations with the molding trials themselves to look at, we're predicting a shearing angle at, at the corner of this extent. Do we see that play out in the molding trials? How can we use that for design? And then as we go through the consolidation process, we've formed, we've consolidated, we've put pressure on. Now we have our consolidated material, which is going to give us the mechanical properties that we need, and using a unit cell model that takes into account all of those mesostructural behaviors, and have that being driven from, maybe a model that we're measuring our unidirectional properties of just the fiber and the matrix as we get those together. How does that play into a coupon that we're cutting from an RFF sample, and how can we validate that this unit cell is going to give us the right behavior, and then bring all of that information into our part performance at the end of the day. So I just want to spend a couple minutes looking through a little bit more detail of a couple of those steps along the way. So one of the things that we're looking at from the unconsolidated RFF material is how do we understand the drapability of this system? For fabrics, typically one of the measures that we'll use for the drapability and the formability of that fabric is a picture frame test. So we put the fabric into the frame, and then we'll pull it, and we'll see what's the force that is required to give us a certain shearing angle of that material. So at some point, you'll see in the figure in the bottom right, we get to a shear locking behavior that happens for a twill or for any other woven fabric where the yarns of the toes are actually going to interlock against each other. They're going to reduce the ability to move against one another, and then it's going to take a lot more force to make that additional shearing happen. That's what causes the wrinkles in our forming process. Well, because we don't have the interlocking behavior in the RFF, we don't see that same increase. There is some increase because of realignment of the toes for the force that's required to continue shearing it, but we don't see a really drastic kind of behavior around like a 25-degree mark. So what this means is that when we move to our forming, we can accommodate much higher deformations, much more complex geometries in our part, and the computational models show that. So we're able to go from our measurements for the modulus of the toe, the friction between toes and between a toe and a molding surface, and use that to model how does our material behave, and use that for when we want to change fiber volume fractions, change sizes of our toes, if we want to go to from a 12K toe to a higher count, those type of things we can explore computationally. And then the next step is, okay, we have this model. We know that as we go through forming, that we're going to have different shearing angles, different different orientation states. How is that going to affect our mechanical properties? So that's where we can use a micromechanical model to develop the unit cell that describes how the RFF is going to behave, and use that to predict our consolidated properties as they are locally to each point in our performance model. So, in the bottom right, I'm showing that as you shear this, the RFF fabric, you're going to have different mechanical properties in different directions based on that shearing angle. One other thing we can point out is because in the RFF system, because we don't actually weave the toes, we can actually start off with different crossover angles of our toes. So our warp and weft don't have to be orthogonal to each other anymore. We can have the warp and weft angled at 45 degrees to one another, at 60 degrees, and we can optimize that initial crossover angle to get better part performance from that. And that's something we can explore with the model as well. But here I'm showing from our prediction model, comparing that to experiments that were done on the RFF cases for the stiffness. We're showing that, if we have a 0-degree crossover, so a 0 crossover angle means that we're at a 0-90 configuration. And then 90-degree crossover angle basically kind of puts everything aligned. And we're showing that at those kind of limit cases, we're matching up really well with the experimental work that we had done to show that we're validating this model. And then also shows to Bob's point, that we're getting very good wet out as we go through the compression process because, as he pointed out, there's not a lot of distance that you have to travel to get the resin to fully impregnate inside the coated toe. So we're showing good results from that as well. And then the last piece is how do we validate our molding trials? So for our molding simulations, we can go through the trial that we just did with this M&T enclosure and take some images of that molded part and then use a image processing technique to be able to pull those flat surface images off of our as molded part and use those to compare with the fiber orientations that we would expect from our simulations. And so that work is ongoing right now to be able to say, okay, how do we validate our fiber orientations? Because that kind of closes the loop on our process. Because if we can understand how the material is going to form, and then we understand how the formed material is going to behave mechanically, then we can, say if we understand which angles our fibers are at, then we have a very high confidence that we're going to be able to predict part performance and use that to drive design, to be able to optimize to the correct fiber orientation, to be able to zero in on the right fiber volume fraction that gives us the right performance characteristics of our part, really have a leg up in our initial prototype to have that good first trial. And so I just want to make a note that this is part of kind of an overarching framework that we're developing at Purdue that I've been leading the effort on lately on the Composites Virtual Factory. So we've talked about the Composites Virtual Factory Hub before. That's our integrated simulation platform that gives us the ability to take all the different simulation tools that are required to be able to understand manufacturing and form performance on a variety of different manufacturing processes. Take those different tools that are provided by a number of our IACMI partner software vendors. ESI, Dassault Systems were two of the major ones that we used on this project, and use those to be able to create these integrated workflows for the different processes. So here, additive manufacturing, injection overmolding or hybrid molding, high pressure RTM, compression molding, those are four of the processes we've really identified as being critical to development of high rate processing for mostly automotive applications, but they have wide ranging uses as well. So being able to create an integrated workflow that uses all this information that we have to be able to drive the design process and give a better end use for our industrial partners. So with that, just wanted to say that the work that we're presenting right now is actually phase 2 of a project that we've been doing with Fibrtec and DuPont. The full recap of phase 1 is available on the IACMI website. We've put together a report for phase 1 that you all can go and see some more information about the coated toes, the RFF, and the simulation process that kind of ties all that together. So with that, I'll turn it back over to the headquarters folks, and I guess we can take questions if there are any.
Thank you, Michael. Appreciate that. This is another one of those exciting projects. Both of them we've got. One, I'm going to open up to questions, but we are at the limit of our time, so I appreciate everybody's participation. If you're interested in staying for the question and answer period, you're welcome to. We'll have it for a little bit longer, then we're going to close the webinar. Any questions? You have to unmute yourself and ask the question, and we'll go from there.
I have a question for Bob Davies. The question is that if your outer third of your toe is coated with the resin, does that give you a characteristic fiber volume of 67%? And if not, then why not?
Okay, yeah, that's a good question. And one of the beauties of our process is we can tailor the fiber volume to whatever you want. That's all done in the design of the process in the dies. So we can do fiber volume fractions anywhere from 45 fiber volume up to 60 fiber volume routinely. We typically set our targets at 3% levels. In other words, 53, 56 are typically the workhorses, and we do some 50 fiber volume fractions also.
Thank you. Any other questions? Okay. Well, I appreciate everybody coming today and listening to this. I'm the Johnathan, Technology Impact Manager. We'll be sending out follow-up emails to this regarding information you can get, and I believe this will also be on our website for use. And I appreciate that. If you have any questions, we'll send them to me, and I can forward them on. So I also wanted to highlight the members meeting that's going on in winter, in January 29th through the 31st. We'll be in Indiana, and we'll have a ribbon cutting at the ceremony for the University of Indiana's Manufacturing Institute, and love to see you there.
Okay, so the members meeting, it's Purdue University's Indiana Manufacturing Institute also is the one where we're going to be having the ribbon cutting at. And members meeting is members only, so I'll be sending, my name is Emily King-Kinsey, should have introduced myself first, and I'll be sending a follow-up email. If you're not currently an IACMI member and you're interested in becoming an IACMI member, just reach out to me and I'll connect you with our membership coordinator who can get you more information about that. Additionally, in January, we have a couple other events. We're going to be participating in the International Auto Show in Detroit, January 14th through 17th for Press Day and Industry Days. So I'll be on the lookout for us if you're going to be attending that. And also, we are hosting a workshop with Composites World at our Scale-Up Research Facility in Detroit on January 17th. If you go onto Composites World's website, they have more information about that. It's cwworkshops.com. Or if you go onto IACMI's website, we have more information about registering for that workshop too.
Thank you, everyone. We'll be having more of these in the future. Thanks.